Time to go to infinity and beyond. Let's look at integrals that involve an infinity, either in the limits of integration or in the function being integrated. And the most basic case, I think, is just where the actual limit of integration is infinity. So let's take a look at something like, let's just integrate from 1 to infinity, something like 1 over x cubed. Okay. Graphically, 1 over x cubed, in case you don't remember or know what that looks like, looks like this, and going 1 to infinity means you are looking for this area. And it does seem like the curve gets pretty close to the axis there, but it never actually touches the axis. There is actual area. There is actual area all the way to infinity. Right? The red line and the blue line are never actually touching. So this just keeps going. And you might think, well, if you're area integrating out to infinity, of course it's going to be infinite area, which isn't necessarily true. Let's take a little side step here just for a second. I don't know if you've ever seen this, but there's a little graphical proof out there that if you add up 1/2 plus 1/4 plus 1/8 plus 1/16 and so on, you know what that adds up to? It actually adds up to 1 exactly if you go all the way to infinity. And the graphical proof that they like to use is to draw a box and say this box is a 1 by 1 box. So it's got an area of 1. So let's shade in the first term. Let's shade an area of 1/2. So there's an area of 1/2. It's half this box. So I've done the first term. And let's add on an area of 1/4. That's half of what's left, right? So there's 1/4. 1/8 is half of what's left. You can see what's happening here, right? You say, how many of these terms is it going to take to fill in the entire box? 1/16 is half of what's left. The next term will be 1/32, which is half of what's left. And it takes all infinitely many, I can't draw it anymore. It takes all infinitely many terms to actually fill in the entire box. So here's a case where it takes, or where you have an infinite number of things added up, and you get a finite result. And so it's not necessarily the case here that when we add up infinitely many Riemann rectangles, that we have to get an infinite result. We could get a finite result. And think about, really, even if I integrated from 1 to 2, that's infinitely many Riemann rectangles, and it does add up to a finite result. Okay, all that to say, the answer to our integral here isn't necessarily infinity. So let's take a look and see if we can handle this integral. And the way that we are going to handle it is with limits. Yay, we get to go back to limits. Because really, limits are the only tool that we have for working directly with infinity. So let me set this up in a slightly different way. I think you'll agree it's going to be algebraically the same. But let's use a different color just to indicate we're doing something different. So I'm going to integrate from 1 to t. 1 over x cubed dx. Notice this is not a u substitution or anything. I'm not changing the x's in the integral. I'm just replacing the infinity with a t with a placeholder. And out front, I'm going to say, let's look at the limit of this integral as t goes to infinity. And I think you'll agree that the result of doing this limit is the same thing as what we have up here, right? These mean the same thing. What this is going to let us do, though, is let us use our integration tools as normal and just plug in 1 and plug in t. And then when we're done with that, we can use our old limit tools from Calculus 1 and actually work out the limit. Okay, so let's switch back to blue and let's see if we can work out this integral. So we have the integral from 1 to t. The limit as t goes to infinity of x to the -3 dx. We'll put it in the calculus-friendly form. And then we'll just integrate like normal. So this will become x to the -2, and I'll put a -1/2 out front. And integrating from 1 to t. This is still the limit as t goes to infinity. But let me get one more step down the line here. So plug in t, plug in 1. So you get -1/2 t to the -2 minus -1/2 times 1 to the -2. And let me simplify this just a little bit. This would be -1 over 2 t squared. I'll just move that back down to the bottom. This is a double negative, so it's plus. And 1 to the -2, 1 to any power is 1. So this just becomes plus 1/2. And even though I haven't been writing it down the last couple steps, keep in mind this is a limit as t goes to infinity. Okay, so now we get to see if we can evaluate this limit. And I don't know how much you remember from back in Calculus 1 about limits, but one of the basic techniques we got for limits was if you have a constant on the top and a variable on the bottom that's getting bigger and bigger and bigger, that term will go to 0. So we do have this whole term right here becoming things like -1 over 1,000,000, -1 over 1,000,000,000, -1 over 10 trillion, which again, that's approaching 0. So that bit approaches 0, which means that overall, this limit is just 1/2. And truly, the area that you are shading in up here, up from 1 all the way out to infinity, that area is 1/2. Which is kind of cool. It's not that often you get to figure out like infinite area and have a finite result. Or at least something, no, I guess I shouldn't say infinite area. I should say maybe like it's got an infinite perimeter, right? If you were to measure around the outside of this shape, you get infinity, but the volume or the area, contained within is not infinite. Okay, let's take a look at a different example. Let's do maybe the integral from -infinity to 2 of x e to the x dx. And I'll just set this one up. I might not do the whole thing all the way through, but again, we need to replace the infinity with a placeholder. So this time I'm going to go t to 2, and I'll take the limit as t approaches -infinity this time. And then we've got x e to the x dx. And now for the moment, we put the limit part on hold. Say, I'll save that till I'm done integrating. And I just integrate this like normal, using t and 2 as my limits. And when I say like normal, it doesn't guarantee that the integral is going to be easy. This, in case you don't remember, needs integration by parts. So you're going to need a u and a dv. And if you remember the liate, e to the x is better as a dv. X is better as a u. So du is 1 dx. and v is e to the x, and you're ready to do your integration. And like I said, here's the part where I don't necessarily need to finish the whole thing out. Well, let's do a little bit of it. I mean, I still probably won't finish it all the way, but we'll do a little bit of it. Just good review. So it's ultraviolet minus voodoo v du. So x e to the x minus e to the x. This is not a plus c because we have limits. So plugging our limits in, first of all 2, and then minus I'll need parentheses around this. And this time we're letting the limit as t approaches negative infinity. Right here, that term, as t gets bigger and bigger and bigger and bigger, is going to blow up. Matter of fact, we could actually factor an e to the, well, it doesn't matter. We can factor an e to the t out of these two terms. And just say, yeah, this is going to get bigger and bigger and bigger and bigger and bigger. So is this, actually. Both of those terms get really, really big. We've got a minus, so we're ultimately subtracting infinity with some finite stuff. So this one actually goes to negative infinity. So that one does indeed blow up. Okay, let's take a look at one or two more examples, and then I will turn you loose on this homework. Okay, so let's consider this one that does not have an infinity in the limits of integration. It just goes 2 to 5. But keep in mind the function itself, if you put 2 in, you get division by 0, which tends to create a vertical asymptote. And if you look at the graph of this thing, it does indeed have a vertical asymptote at 2. So the function itself goes to infinity in the context of this integral. So that means we still need to treat that 2 with a placeholder. So I'm still going to turn this into the limit as t approaches 2 of an integral from t to 5, and then 1 over square root x minus 2, or maybe I'll change this into a little more calculus-friendly form again. Okay, and we're ready to do the integration. Again, we'll kind of put the limit on hold. We'll ignore this part here until we're done integrating. This does require a tiny little u substitution. U needs to be x minus 2, and du needs to be dx. So when we integrate, we get the integral of u to the negative 1/2 du, which becomes 2u to the 1/2, and u is the same thing as x minus 2. And we were evaluating that from t to 5. So when I plug in 5, I will get 2. 5 minus 2 is 3. To the 1/2 minus 2 t minus 2 to the 1/2. And we now need to take the limit as t approaches 2. Keep in mind the first thing we always try with limits, if we can, is just direct substitution. Direct substitution wouldn't have worked on the original because x minus 2 was in the denominator. Turns out x minus 2, or t minus 2, is not in the denominator anymore. It's in the numerator. And I can just plug in 2 for t and get 0. 0 to the 1/2 is 0. That's fine. No domain issues there. So this limit is equal to 2 Maybe I'll go back to square root just for fun. 2 square root of 3 minus 2 square root of 0. So just 2 square root of 3. Okay, I think I'll do one more example and then we will be done. So the last example I wanted to give you is just, let's say you're integrating something like 1 over x minus 2 from 1 to 5. And as you know, 1 over x minus 2 does have a vertical asymptote. It's at 2. It's not at one of the endpoints of the integral, unlike last time. We do still have to be careful about that infinity in the middle, and that means we're actually going to have to break this integral into 2 separate pieces. We're going to have to do the integral from 1 to 2, so we're going to have to break it at the problem point. And then we'll add to that the integral from 2 to 5. For both of these integrals, we're going to replace the problem point with a t. So this will be like a limit of 1 to t. And this one also has a problem. So we've got 2 separate integrals. They both have a problem at x equals 2. So I'll add to that the limit as t approaches 2 of the integral from t to 5. And I'm not going to finish working each of those integrals out. They're tiny little u substitutions, and then you'll do your limit as t approaches 2 on both of them. Turns out, well, I'll let you figure it out. But yeah, I just wanted to remind you of that idea that in general, when t goes to infinity, things like 1 over t, so yeah, the limit as t approaches infinity, 1 over t. So this is just not related to this problem anymore, but just the general principle that as the numerator gets bigger and bigger and the denominator does not, that goes to 0. And then I'd also like to remind you, just in case you need it, that you can go to the hospital if you need to. L'Hopital's rule is also good for limits that come out either in that form or in that form. And L'Hopital's rule says if you have that form or that form, you can take the derivative of the top and the derivative of the bottom separately and try the limit again. All right, this is turning into like an 18-minute video. Might be my longest one yet. I just got in a groove. I couldn't be stopped. Sometimes you have calculus in your soul, and all you can really do is try to hose yourself down and keep going. So, all right, good luck with these integrals, and we will move on to the next chapter.